Okay guys, so today we're going to do problem 5.5 in the textbook. So the question reads, calculate the magnitude and direction of the force exerted by the pipe bend shown in plan view in figure 1. If the diameter is 100 millimeters, the discharge is 0.03 meters cubed per second, and the pressure head is 20.387 meters at both the inlet and outlet. Water flows in the pipe in the direction as shown. Alright, so it's clear here the question is not entirely the same as the one in the book of C.F. Mayer. You'll see that the discharge he uses is 30 liters per second, and he uses a pressure at both the inlet and outlet as 200 kPa. So that the pressure head, 20.387 meters, is just simply converted using our formula, which I will show you now. Okay, so we have this rho G H is equals to the pressure divided by rho G. So that's how I got to this value. Okay, so that we have. So we don't want that on our sketch. Okay, so first of all, remember when we work with conservation of momentum, conservation of mass, and conservation of energy, we have to know what we're dealing with. So first of all, we know that they're asking us the magnitude and direction. Okay, magnitude and direction, so we have to go and convert things to velocities, and we have to show our pressures and all of that, and also of the force exerted by the bend shown. So we need to calculate the magnitude and direction of the force exerted by the pipe bend shown. So we will have an external force that we have to indicate, and normally I tell you to assume it in this way. I'm going to try my best to draw it here for you. So we have our Fe, which you will normally assume as such. Even though it doesn't make sense to you, I know that you feel that this arrow should be in this direction, like so. And that's not the case. You will see later on when it comes to the sign, doing the signs, why it's important to have it in this direction. So let's just get a better arrow in there. And we also have to show with the angle that we're going to calculate. Let's call it alpha. Alright, and this will be our Fex, and this one will be our Fey. Okay, and this one will be our Fe. So that's the first thing that you can start with when you do this. So first of all, we know that there's a discharge. So if there's a discharge, we know that there will be a velocity in the direction of flow. So we have velocity 1. And we will also have a velocity going out. In this case, it will be in the same direction as flow, and that will be V2. Okay, and now because we know, let's do pressure. The pressure will be in the opposite direction of flow because the pipe continues. This symbol here shows you that the pipe is continuing. Okay, so let's call this pressure at point 2, and here at point 1 or the inlet rather, pressure 1, and that's also in the same direction of flow. So far so good. So normally you won't be this lucky, you won't normally get this. This was just to help you, to show the sign convention. So you'll normally do that on your own. But for this question, I've added it for you. So we have our direction, our Y, showing upward as positive. So we can give it our sign convention. We can say Y upwards is positive, and in the X direction to the right is positive. Remember, that becomes important when we're going to work with our sign conventions for the velocity and the pressure. Alright, so what's the first thing we can do? We can calculate the velocity V1. Right, so that's the first thing that we'll do here. So let's see, let's calculate velocity 1. Okay, so first of all, we know the formula reads that Q is equals to A times V. In this case, it will be V1 and also A1 and Q1. But this is also equal to Q2, the discharge at point 2. Why? Because D1 is equals to D2. Okay, that's why. And because of the conservation of mass, where we say Q in is equals to Q out. Okay, Q in equals to Q out. Okay, so now we can do this. So we know the discharge is 0.03, and we know that the area, that's something that we'll have to calculate. So it's going to be pi d squared, which will be 0.1 squared divided by 4 times our velocity 1. So if we calculate this, we will end up with a form of a value that we have to quickly calculate. Alright, so you can simply go and say 0.03. Remember to use your stored values on your calculator. 0.03 divide by shift pi, and you will see if you've calculated correctly, that should give you 3.819 meters per second. Okay, so that's your first answer, and you'll get 2 marks for something like that. Okay, it's pretty simple. So here you can say that this is now V1, because the diameters are the same. V1 is equals to V2, and therefore this is also equals to 3.819 meters per second. Okay, so that's the first thing that you can do, which is just pretty easy. So now we can move along. Okay, so now we need to calculate, in this case, the pressure, because we will need it later on. Okay, so we simply go and say in this case we have the 20.387 meters. So again, you could have just used the formula where we have our P1. Remember, we said that the question reads that the pressure head at both the inlet and outlet is the same, basically 20.387 meters. So meaning we have this, rho G is equals to over rho G. Okay, and that pressure head is equals to 20.387 7 meters. Okay, so if we have to go and calculate, the pressure now, P1 is equals to P2, that will be equal to 200,000 Pascal. Okay, so we've got that down, another 2 marks. So now you need to note, so the pressure forces from the control volume shown. So have we done our control volume? Yes, I've given you the control volume here. This is the start of the control volume. So it shows you that the pressure at point 1 produces a force in the positive x direction, and there is no other pressure in the x direction, so the component of force in the negative x direction is 0. So similarly, in the y direction, pressure at point 2 produces a force in the negative y direction only, so the positive y component is 0. Okay, so it's just simply saying what we have is a pressure in a y direction, a pressure in an x direction, and so on. That's basically what is being said. Okay, so now we need to start with our momentum equation. So let's start with it here on the side. So what does the momentum equation say? So we can say we're going to start with the conservation of momentum. Okay, so now you know, okay, I need to do conservation of momentum. And conservation of momentum reads that the sum of the forces in the x direction should be equals to the mass flow rate times the velocity change in a certain direction. So in this case, it's the x direction. And we know that mass flow rate is equals to rho q. Okay, and we will have our velocity 2 in the x direction minus our velocity 1 in the x direction. Close the bracket, and that's it. And we take x to the right as positive. Alright, so now we know, okay, let's do our forces first. The sum of the forces in the x direction. So what will we have? Okay, so remember to calculate a force, so take note, pressure is equals to force over area. So therefore this, if we have to do a force calculation, force is equals to P times A. Okay, so we'll have to do that. We'll have to write the sum of the forces. So let's do that first part. The sum of the forces in the x direction will be equals to, if we look back at our figure, the forces in the x direction, we have the pressure one, which we have to write in terms of a force, this guy here. That's one we're going to use, and also we're going to use FEX in our calculation. Okay, so let's just delete those circles, don't mess up. So let's do it. So the first one is going to be our pressure, the pressure 1x. It's going to P1x times the area in the x direction plus P2. There isn't any force in that direction, but we could have added it. So, but just for argument's sake, let's add it in there. But it won't be, there isn't any force at point 2 in the x direction. Okay, so we'll have P2 x and A2x. Plus our FEX. And that's about it. So let's quickly calculate this one and see what do we get. Let's see. Okay, so the pressure at 1 will be the 200,000 Pascal times the area. The area again, which will be, you could have used pi r squared. In this case, let's use the diameter, 0.1 squared divided by 4. Okay, and then we have our first force plus 0, because we don't have any pressure force in the x direction at point 2, and plus FEX. Okay, so let's quickly simplify this one so we can get some values out of it. Okay, so remember you should have stored this guy in your calculator as your A value. You might use it later on. So let's do the 200,000 kPa times that area of the pipe. And that gives us a value of 1570.796 plus FEX. So you can't give it units or anything just yet. You're going to use this later on to combine the FEX equals to rho G F2X minus V1X. Okay, so now we have to do the right hand side of the equation. This side of the equation, the right hand side. So let's do that. So it's firstly it's going to be our rho Q V2X minus V1X, and that's going to be equal to the density of water, in this case would be 1,000, times our Q, which we have already as 0.03. Just add the multiply sign there. Put that in brackets for yourself and add some more brackets. V2X. So remember V2X, if we go back to the figure, V2X, is there any velocity in the x direction? No. So we can say that is 0 then. Minus V1X, we know for a fact that is a velocity. So, and we know it is equal to the 3.819. 3.819. Okay, so now let's quickly calculate that. Remember to also store these values so it will help you later on. You could store this in B. Okay, let's do the second part, so which is 1,000 times the 0.03, close the bracket, multiply bracket 0 minus 3. That value that you stored, which will be alpha A, and that should give you a negative 114.591. Okay, so that is correct. .592 rounded, So now we have our equation. Okay, so let's store this value as well. Let's store this in C. Okay, so now we can equate, we can say, so in essence this will be 1570.796 plus FEX is equals to a negative 114.592. Okay, so therefore we can calculate FEX now. So which is simple. So we'll simply take the negative 14 that you stored in alpha C minus your value that you stored in alpha B, and that should give you the following: negative 1685.388. Okay, and it's a force. So it means that FEX, the FEX that we assumed earlier on. So if we continue this here on this side, so we know now that FEX is equals to 1685.388 newtons in positive to, let's just check again, what did we say? We said it's now positive to the left. So it means that FEX, this FEX we assumed here is incorrect. It means that FEX is actually in this direction. Okay, see why it's important to do it this way? Then you know, okay, that's the true direction of FEX now. So now we can continue. So it's to the left. Okay, and now we can move on to our second part, which is the sum of the forces. Let's just close this off. So this is FEX, this part here. So let's do the same thing now, exactly for the forces and the velocities in the y direction. Okay, so we have the sum of the forces in the y direction is equals to, again, rho discharge times V2y minus V1y. Okay, let's calculate the sum of the forces in the y direction. So let's do the left hand side of the equation first. So what will that be? So if we have a look at the sketch, what do we have? Do we have any forces in the y direction here? No, we don't. We only have forces here, which is P2, which we have to convert, and we only have, so basically we only have this guy and FEY. We don't have any other forces or velocities in that direction. We only have these three. Okay, so let's just quickly delete those circles. And let's continue. All right, so we know that it will be the pressure at point 2 times the area at point 2, and it's in the opposite direction. So remember, we said upwards is positive, so this will be negative. So it's negative P2 times A2. and that will be plus our FEY, which is upwards. Okay, and that's about it. Only for the left hand side. We're working with the left hand side of the equation now. Okay, so let's do that. So we'll have a negative. The pressure again is 200,000 Pascal times the area again, which will be pi d squared, which will be 0.1 squared divided by 4. Close the bracket. Another bracket plus FEY. So let's solve quickly. So, and remember, now we almost forgot we had to store this value here in D. Store that value in D because you need it to calculate the resultant later on. But remember just to change it to a positive. So you'll multiply it by a -1, so you can just make it positive, then store it in D. Shift store in D. Okay, so in essence you need to store this guy, the +1, store in D on your calculator. Okay, so let's do that calculation. So it's going to be the 200,000 Pascal times the area again, of the pipe, okay, and this will give us a -157.796 plus FEY, which should make sense because if we compare it to the other one where we had 157, this one here, if we had to compare it to this, it's almost the same, which makes sense except for the sign now, because the diameters are the same and it's a 90-degree bend. You can see it from the sketch. It shows you as well. Okay, so then once you've done that, you can start with the right hand side of your equation. So let's do the right hand side where we have our density times discharge is equals to our V2y minus our V1y. That shouldn't be equal there. Okay, so we have this. So let's calculate that. So it will be 1,000. So we're working with the right hand side of the equation now. We're working with the right hand side. So it will be 1,000 times the discharge, 0.03. Put that in brackets for yourself. And V2y. Now let's check. We know that V2, there is a V2 in the y direction. If we go and look at the sketch. Here we have, so this is in essence V2y, because V2 is in the y direction. Okay, so pretty simple, so let's do that one. So it's going to be V2, and we've stored V2 already, and we know that V2 is equals to this guy here. It's highlighted for ourselves. We know this is V2. So we're going to have to use alpha A here. Okay, so let's do that. So it's going to be okay. Just before we go on, just want to store this value in A, B, C, D, E. Store this one in E. Should have told you. So this value, just store it in E on your calculator so you can use it again. Store in E. Okay, and now we can use our velocity V2y, which is 3. Yes, don't worry. 3.8. 3.81. Let's go. Check on our calculator. 31319. Okay, so it's 3.819, and that's in the positive direction. So it stays positive, and then minus our V1y, which we don't have. There isn't any V in the y direction at point 1. So this is point 1, this is point 2. So there's no V in the y direction. There's no V here in the y direction. There cannot be. Okay, so therefore it will be 0. Okay, so we simply just say 0. And we close it off and we calculate. Okay, so let's do that. So it will be the 1000 times 0.03, close the bracket, times your bracket 3, okay, in this case alpha A minus 0, and that should give you a positive 114.592. Okay, so now we can write out the equation because we've got both sides, the left hand side and the right hand side. So here we have, we're going to have on the left hand side, we're going to have, I'm going to write it the other way around. So I'm going to write it, okay, let's do it this way. Let's do it the right way. Negative 1570.796 plus FEY, so that's my left hand side of the equation, is equals to the right hand side, which is 114.592. Okay, so now we can solve for FEY. So let's do that. So it's going to be simply the value that you just calculated, the 114 point. You could have stored it. I've just got it still on my display on the calculator. So you can take that and say, if we take this value over across to this side, what's going to happen? It's going to become positive, right? So we add it to the 114. So it's going to be plus, or you can say negative, because remember you stored that as a negative in your calculator. So you have to say, this is where you can maybe make a mistake. So even though this sign is a negative, you can maybe rather see it as, if you've stored it here as a negative, then, and you want to take it across to the other side to minus, you still have to use the same sign. It's going to change to positive, but you have to be careful. So let's use it as we stored it. So we'll say, basically, we'll assume that this is in brackets. We'll assume it's in brackets. We'll take it over to the other side. So it will be the 114.592 minus our alpha E. And yes, that should give you 1685, a positive. You'll see that your calculator will give you a positive 1685.388 newtons. And that, people, is basically the part that you want. And you can store this in what did we use? We used E, so we can store it in F. Store this in F on your calculator, and now you can simply go and calculate the resultant force using the following two formulas, where you say Fe will be equals to the square root of Fey squared plus Fex squared, and you'll calculate alpha, which in this case will be arctan, where we have Fey over Fex. And that should give you Fey, if I could squeeze it in here, Fe rather, should be equal to 2.383 kilonewtons. And your alpha should be equal to exactly 45 degrees. Okay, and that's the problem, and that's how you solve this question. And then if you want to, you can add onto your sketch what you've done. And that's it. Thank you.